mean variance portfolio theory, CAPM and APT, asset pricing model, or asset pricing theory. So, what is one of the most important discovery of the last several decades is the fact that now we can quantify risk. So it was not possible before the 60s, early 60s, now it's possible. And the implication of being able to put a quantitative measure of risk on risk is that we can value now different classes of securities. And we can also assess the relationship between risk and return much more appropriately than before. And that's exactly what we are going to do in this first topic. We are going to talk about the relationship between risk and return. So in order to understand that, and in order to understand the mean variance theory, let's start with very simple concepts of the expected value and the standard deviation. And then for one asset, and then we'll move to the discussion of the expected return and the standard deviation of returns. And then for one asset, and then we'll definitely continue with the multiple asset portfolios of two, multiple meaning two assets first and then more than two assets, okay? So that's what we are going to discuss in this topic. So let's start with the expected mean, expected value or the mean value of a random variable. So by definition, it's something that you're supposed to take a statistics course, so I believe that you understand what I'm talking about. The expected value of a random variable, by definition, is what? Is the sum of the probability of a certain value of that random variable to occur times the value of the random variable, okay? Because the random variable can have different values, it's the probability of each value taking place multiplied by the value of the value of that outcome. Now, this leads, or the expected value has the following properties, and these are very important because we'll see where some of the properties of the...
May I have your attention, please? This is Fire Light Safety Director. We are conducting a test of the Class E fire system. I repeat, we are conducting a test of the Class E fire system. Please disregard all bells, sirens, and horns that you may hear or see. Thank you.
Okay.
What is the variable piece of I in that zone?
What is it?
In the very first line, the expected value.
Mm-hmm.
It says piece of I sub x sub I, or
Here?
what is, yeah. What is
I
piece of
equals
in-
1
no,
from
what is P in this?
the probability of that value.
The probability of
Yeah.
Okay.
Okay? So we are going to look at these properties. Why? Because you recognize some of them when we discuss the expected return of a portfolio or the standard deviation of a portfolio, okay? So let's see how, if you add a constant to a random variable, as you can see, the expected return is what? Is the constant plus the expected return of the variable. That's the first property. If you multiply a random variable by a constant, the expected value of that product is what? Is the product between the constant and the expected value of the random variable. And finally, if you have two random variables and you want to compute the expected value of that, in other words, the expected value of a sum of two random variables is the sum of the expected values of the random variables, okay? So I'll show you how to derive some of these properties, and then we'll see the implications of these properties into the returns of an asset. So let me see what would be the best way. Okay, so how do we show that the expected return of a sum between a random variable and a constant, in fact, is the sum of the constant plus the expected return of the random variable, the expected value of the random variable? Well, we start with a definition. What is the expected return of a random variable plus A? according to the definition, is what? Is the sum
Probability.
of pi times what?
Random variable.
xi plus a, right? So I just applied the definition. Now our random variable x is replaced by x plus a, but a is a constant, therefore it doesn't have a subindex. The only thing that has a subindex can take different values is the random variable. Okay? And this goes from 1 to n. We already know that the sum of a sum, in fact, can be broken down into two sums. So this would be, the first one would be pi xi, and the second one would be pi a. So far, so good? Okay. Now, this, by definition, is the expected return of x. Right? Yes, sir.
Does the random variable represent the unsystematic risk? Risk you can't predict?
It's just a random variable.
Just random?
Yeah, it's just a
'Cause
random
that's how I
variable.
thought I
Not-
understood it.
Return is a random variable.
Okay.
A start return is definitely a random variable because you cannot predict it. So random, it's something that you cannot predict. Okay? So, for example, your test scores at the end of the semester. This is the student test score. It's a random variable because I have no idea what will be at the end of this semester. Okay? The temperature, it's a random variable. I have no idea what the values of the temperature tomorrow, the day after tomorrow, and so on are. That's a random variable. Rolling the dice, the values are a random variable because I don't know what, if you roll a dice, I have no idea what will come. So is that clear now? This is
Yes.
what the random variable
Yes,
means. So
it's clear.
it means a variable whose values are unknown. Okay, cannot be predicted. Like the stuff.
Yeah, because I just thought that this was a way to set up the CAPM, but now I see it's different.
It's not yet.
Okay.
Yes, it's a way towards that, but not yet.
Okay.
Okay? So far so good?
Yes.
Okay. Now, what about this one? Well, because a is a constant, it can come in front of the sum. And this can be written as what? As a sum of pi,
Which is 1.
but pi is absolutely, you're right, absolutely right on it, is 1. And why is that? Because we know that when a random variable takes different values, the probabilities associated with different values will always sum up to 1. For example, let's say that in a classroom we have 10 students that would score an A, and 20 students that would score an A minus, and 5 students that would get a B plus. Okay? Well, what would be the probability to get an A in that class? It's 10 over the whole, right? So 10 pi is 10 over 35. What is the probability of getting an A minus in the class? It's 20 over 35, right? And what's the probability of getting a B plus in the class? 5 over 35. Now, if you look at all these probabilities, if you sum them up, they always equal to 1, because this is how they were formed. Okay? So, if we factor A in front of the sum, what we have left is the sum of the probabilities, but the sum of the probabilities are always, it's always 1. Okay? So what we are left in the derivation is what? Is the expected return of the random variable plus A times 1. So finally we have expected return plus A. Exactly as we want to prove. So we want to prove that the sum, the expected value of a sum between a random variable and a constant is the sum between the expected value of the random variable plus the constant. Okay? So far so good? Okay. What about the second one? So how do we show that the expected value of a product between a constant and a random variable is nothing else but the constant times the expected value of the variable? How do we show this? We start again with the definition. So we know that the expected return of this product is by definition what? The sum of PI times what? Look at the definition.
Random variable.
So if it's just X, it's PI times X, XI. But if I get an A in front of X, what do I put in under the summation sign? So what do I put in?
I think you put A before the summation sign. I think you
Well,
put A-
before I put A before the summation sign, what do I put inside here? So what I'm doing here, I'm replacing X by what? By AX, right?
Right.
So if I'm replacing X by AX, what will be on the right hand side?
I think the X.
AX.
The variable.
AXI,
AX, yeah.
right? So if I replace, it was, by definition, the expected value of X is sum of PI XI,
That's it,
right? This is the definition.
right.
If I replace this by AX, then I need to replace this also by AXI,
Right,
right?
right.
That's exactly what I've done here.
Mhm.
A comes in front of the summation because it's a constant, so it would be A sum of PI XI.
Yeah, right.
And what is XI, sum of XI PI times XI?
Expected.
It's already the expected value. We know that this is the expected value of the random variable, right?
Mhm.
So therefore,
A.
we prove what we want to prove. The expected return, the expected value of A times X is A times the expected value of X, right? So far so good? Yes, no, maybe?
Yes.
Yes.
Okay, let's do one more. Maybe-
I've got one more detail on my phone. We started by saying piece of I was a random probability.
Piece of I. Where's
Piece of I. Piece of I. The probability, P.
P. Okay.
Right. But,
P is not random. P
yes,
is the
that's what I was
probability.
just about to get. You just showed the example, your,
Mhm.
10, 25, whatever. The sum of the piece of I's have to total up to one.
Mm-hmm.
Okay, so that was confusing me, the difference in definition there. But I'm missing some, why did piece of I have to sum up to one, other than we said so? We never seemed to put that as input into this. That wasn't the property we talked about.
Well,
We said,
for a
let's
random
detail.
variable, regardless of the values, the probabilities with which a random variable takes different values will
Yeah.
always sum up to one. That's one of the properties of a random variable. Okay, that's something that, in a way, I take from statistics, something that you learn in a statistics class. Okay, so whenever if you think of the easiest connection you can make, and we'll make that connection in a second, is with stock returns. How do you compute the expected return of a single stock? There are many ways, one of which is if you know the states of nature, right? Boom. If you teach CAPM and risk and return at the undergraduate level or the graduate level, this is one way to show it. So it's the states of nature are boom, normal, and recession, right? And each of these states of nature is assigned a probability of occurrence. And let's say that the boom will have a probability of 20%, the normal 40%, and the recession is what?
20.
Well, is the
60, 40.
difference between
40.
100% minus the sum of the other two.
Right.
Because you cannot have anything else but a boom, a normal, and a recession, since these are three different exhaustive states of nature, right? So this is where the fact that the sum of the probability is always one. Because these states of nature, or the values that a random variable takes, they are all exhaustive. They cannot be anything else. Therefore, the probabilities of occurrence of these values will always sum up to one.
Okay, so each x of I is a state of nature then, regardless of
You
how many
can,
I we have.
no, each I is a state of nature.
Okay.
Xi is the value in that state of nature. If you want to think of it this way, yes, you can think of it this way, if it makes more sense to you. So far, so good? Is it better? Okay. And the last one is the sum. So the last one is the expected value of a sum of random variables is nothing else but the sum of the expected values. How do we prove this? And then you see immediately the application of that, of these properties. So the expected how do we prove this? Well, we once again start with the definition, right? So remember, the definition is the expected value of x is sum of pi xi, right? Now I replace x by what? By x plus 1. Therefore, I have expected value of x plus y equals, by definition, pi. And what do I put after pi?
X plus Y.
Xi plus yy, right? So I replace x now by this sum, therefore I replace xi by xi plus yy. Make sense?
Yes.
And now I break it into two sums, into this sum of pi xi plus sum of pi yi. Well, but each of them is what?
By definitions.
It is a definition, is the definition of the expected value, right? Right? Now, what is the implication of all these when it comes to returns? Because this is the goal of our topic today. Well, remember that one property we had for the expected return of the portfolio was what? Was the fraction invested in, let's assume we have two stocks in the portfolio. And the expected return of the portfolio is the weight of the first stock times the expected return of the first stock, plus the weight of the second stock times the expected return of the second stock, right?
Mm-hmm.
And we do this for granted. But in fact, this property comes from these properties. Why? Well, because in fact, the return of a portfolio is a random variable. How is that portfolio formed? By allocating W1 to stock 1 and W2 to stock 2. In other words, this is nothing else but W1 R1 plus W2 R2, right? That's the way we form the portfolio, by allocating different fractions to different components of the portfolio. In this case, we have only 2. In other words, we have here, let me write it somewhere else. So we have the expected return of the portfolio is the expected return of W1 R1 plus W2 R2, right? We already know that the expected return of a sum
Is expected.
is the sum of the expected returns. So in other words, if I consider this x and this y, I can already write this as the expected return of x, which is W1 R1, plus the expected return of W2 R2, right? Because this was the x and this was the y. Do you follow me?
Yes.
And if I now apply this property, I can take the y's out of the expected value because the fractions, the weights are always constant. So therefore I can write this as W1 ER1 plus W2 ER2. We started from here and we got here. And that's exactly the expected return of a portfolio formula that we use when we teach risk and return, but we never think where it comes from. Well, it comes from these properties of the expected value of a random variable. Make sense? Questions? Yes,
Why do you
Ed?
need to organize it? Why couldn't you just stop on the second level?
What do you mean second
In
level?
other words, I understand, you know, it's the weighted average returns equal to portfolio. But then I noticed that in the research also, that then they'll reorganize it. So you put W1 ER1 plus W2 ER2. Why, God bless you, why do you need to do it? Why do you need to do that? Why couldn't you have just stopped at that?
Here? You mean here?
Yes. Why did you go the next step?
Because it's much easier to read it this way, because you already know how much you invest in each stock.
Right?
Therefore, you want to separate the allocation,
You
the
want
stock
to,
allocation from the expected return of each.
you want to premiere the weighted average is what you're saying.
Yeah,
Okay.
because you want to show, I think, in fact, you put the dot on the I, you want to show that the expected return of a portfolio, it's a weighted average
Yeah.
of the expected returns of each
You
component.
want to
in it.
feature that, and that's.
If
what-
you stop here, you don't see that,
Right.
right? Okay, so far so good?
Yeah.
Perfect. Let's move to the properties of the standard deviation, or in fact variance of a random variable. You know what surprises me always? How come this is cheaper than water? So we don't have water, bottles of water, because they are more expensive, but this is cheaper. Isn't the can more expensive than water?
Research paper.
Probably talk to the marketing people about that one.
Yeah. Anyhow, so how do we define the variance of a random variable? And the definition is the probability of each value taking place times the deviation from the expected return squared. This is something that
Very.
you might have seen. I'm not, definitely if you teach risk and return, you apply it constantly when you calculate the standard deviation of a stock returns. Okay, but this is not for a stock return, this is for any random variable. So the variance of the random variable x is the probability of each value of the variable taking place times the deviation from the expected return of that value squared. Okay, this is the definition. Now these are the properties of the variance. This is the definition of the variance, these are the properties of the variance. What do the properties say? If you have a constant added to a random variable, the variance of that sum is just the variance of x. In other words, A doesn't matter whether you add or you don't add to something that moves randomly. It doesn't change the randomness or the variance of that random variable. Okay? That's the first property. The second one, and we'll show it in a second. The second one says what? Well, if you multiply a random variable by a constant, the variability of that random variable multiplies by the square of the constant. So the constant magnifies the movement of the random variable. Okay? And then last, if you have two random variables, the variance of the sum is the sum of the variances plus what's called the covariance between the two. And the covariance is defined as what? As the expected return of the deviation from the mean for the first random variable multiplied by the deviation from the mean for the second random variable. Or, if you really want to see it in a different way, this is also sum of pi, xi minus expected return, times yi minus expected return. And let's keep with the notations. So this tilde is another way to show you that that's a random variable. In other words, it's unpredictable. Okay? Now, let's prove these three, and then I'll let you look at, once we do this, I'm sure you'll get an idea how to do the rest of these properties, and I just show you the implication of these properties to asset returns. So how do we show that the variance of a random variable plus a constant equals to the variance of the random variable only?
It's constant variance, there is no, it's always 0.
So variance of x plus a. How do we prove this? Well, we start with the definition. So in this definition, we replace now x by x plus a, which means that xi will be replaced by what?
X.
Xi plus a, and this x here will be replaced by x plus a, right?
So square.
So therefore, we have the variance of x plus a will be sum of pi times what?
X plus A.
Xi plus a
Right.
minus the expected return of
X plus A.
x plus a.
Right,
Okay, square, right?
that's the variance.
Okay. So far so good? Okay. However, we already learned something about this expected return. When we have this expected value, when we have the expected value of a random variable plus a constant, what do we know about this?
So A will go out as a plus A.
The first property we just learned.
Mhm.
This is nothing else but the expected return of the random variable plus a, right? Therefore, the whole thing is pi times what? Xi plus a minus expected value of x minus a, because I have the minus in front of the expected value. So minus this is minus expected return of x minus a squared. Right? A and a we cancel out, and I get sum of pi xi minus expected return squared. And this is nothing else but the variance of x. Okay? So we do nothing else but apply the definition over and over and over again. And substitute x in the definition by whatever we have to prove. So in this case, we substituted x by x plus a. In the next derivation, we'll substitute x by what? By a times x. And in the last one, we'll substitute x by what? By x plus y. Okay? Do you still follow? Are you still with me? Okay, so next var ax is a square var x. How do we prove this? In the definition, we replace x by ax, which means that xi will be replaced by what? AXI. And x here will be replaced by AX. Okay? So, var, the variance of AX will be by definition sum of PI times what?
X.
AXI minus expected value of
X.
AX squared. Okay? If it's easier for you, I'll put square brackets such that you understand where some brackets start or parentheses start and where some end. Okay, now based on a property we have already gone through, we know that the expected value of AX is what?
A will come out.
A
Expected.
EX, right? This is the second property. The second property we just learned, right here. So now we apply this property and replace expected value of AX by A times EX, right? Therefore, this would be sum of PI multiplied by AXI minus AEX squared, squared. So far, so good? Now I have A for both terms in parentheses. I can factor it. And I can factor it all the way out of the sum because it's a constant, not a variable. Okay? So this would be A times what? Sum of PI, XI minus EX
Right.
squared. Right?
Yes.
Well, but this is nothing else but the var, sorry,
There.
one mistake. I squared it, I factored it, but I forgot that that was squared. So when I factor it, I need to square it, right? So that should have been A squared. So, and this is nothing else but var of X. Yes, sir.
Are there times when we look at, why would we look at absolute variance?
Because there is no way you can measure, as you can see, at least in the mean variance portfolio theory, there is no way you can get the standard deviation directly. So you need the variance in order to get the standard deviation.
'Cause I see-
Variance is also a measure of risk.
Right, yeah, absolutely. But sometimes I see that they talk about finding the absolute variance, not squaring it. Why would that be helpful?
Because absolute, when you square the deviation from the mean, what's the reason for that? If
To
you
get,
don't-
so you don't have them canceling each other.
Exactly. If you apply the absolute value, it's exactly the same thing.
No, but that's why I'm curious, because lately I've been reading about using absolute variance.
Because it's exactly the same thing. So the only reason for squaring this deviation from the mean is to simply avoid letting variables canceling out each other. But if instead of squaring it, you just say, let's say, XI minus expected return in absolute value, that has exactly the same.
And you know what, it might also have been in relation to when you're looking at just the potential loss. So maybe they were all negative, they wouldn't cancel each other out, I'm not sure.
But that's exactly what I'm saying. So
Yeah.
if you do an absolute value, this will always be positive, exactly the same as this one.
Right.
If you square it, it's always positive. If you do the absolute value, it's always positive. There's no way they can cancel each other.
Right.
But the calculations are easier because you don't have to square numbers. You can see them. You have a feeling of the a better feeling of the numbers.
That's it.
Yeah. So that's the reason some use this as a measure of risk instead of absolute value of the deviation from the expected return. It's not too common, but it's used.
Okay.
Okay? Yeah, John.
You're squaring the formula, but I feel like you're missing adding up some of the terms. We actually mechanically did.
I didn't square anything.
Well,
I didn't square anything, John.
but to remove the A,
Mm-hmm.
we squared it. But A is used under two different terms here.
Mhm.
Why is there not something that is, again, if we did square this, there's gonna be a middle term in there.
I didn't square anything. I just factored this out. So let me show you what I've done.
But
So
when
I
you factor it
factored.
out, you factored out squared, right?
Yeah, so I factored it out here. Let's say that we copy the properties. I factor it out in the parentheses, xi minus ex, and that was squared, right?
Yeah.
I skipped one step, but I thought that was unnecessary. I'll add it if that's better. So let's assume that I'm filling in the missing step, right?
Mhm.
So what should I have done here? Factor A in parentheses here before I square it. So it's A times xi minus ex, everything squared, right?
Mhm.
And now when I get it out of the square brackets, it has to be a square. Okay?
Okay.
So this is, I didn't square anything, I'm just taking out the constant of the square brackets.
Okay,
And this is what led to the next step,
got it.
okay? And this shows that, looking at the last step, this is nothing else but a squared var x. Exactly what we wanted to prove. So we started with the variance of a times x, and we showed that that is a squared times the variance of x. Okay? And last, and then I'll show you why we need these properties of the variance, is the var of x plus 1. So we apply once again the definition. How? We replace x in the definition by what? We replace x here by x plus y, right? Because I want to show the last property, which means that I replace xi by what?
X plus y.
xi plus yi, and the x here, I replace it by what?
X
By
plus
x
y.
plus y, okay? So this means that the variance of x plus y would be, by definition, sum of pi
Xi
times what?
xi plus y.
And you use square brackets. Xi plus yi minus
Expected. X plus y.
square, right?
Right.
Well, we already know that the expected value of the sum is what?
Expected x plus expected y.
From the third property, we know that the expected value of the sum is the sum of the expected values.
Right.
So this would be,
Expected x plus expected y.
and I copy everything else, xi plus yi, and I write this as expected value, let me put it in parentheses, expected value of x plus expected value of y squared. Okay? So far so good? Now, what do I do here? I pair this with xi, and I pair this with yi.
Right.
And I have what? I have sum of I equals 1 to n pi xi minus expected return, well, minus expected value, plus yi minus its expected value. So I couple this with the first one, and the second one with yi. So far so good? And now what do I do? Now I square them. So this is, let's say, A, and this is B.
A plus b squared.
And I use A plus B squared. What is A plus B squared?
It's the line.
A squared.
A squared plus B squared
Plus 2ab.
plus 2AB, right? That's exactly what I'm doing. So it would be I1 from 1 to n pi of, and I'll put square brackets here. It would be I squared, which is xi minus ex squared. That's A squared.
B squared.
Now I'll square the other one.
yi expected
Square, right? And last,
plus
2xi minus ex times yi minus ey. So we did nothing else but simply using the formula a plus b squared is a squared plus b squared plus 2ab. Right?
Base row.
That's the formula, algebraic formula. We don't invent the wheel, we use what has been already discovered, right? So, why do I use this? Because now let's break this big sum into 3 smaller sums. And we have the first one would be sum of pi xi minus ex squared. This is the first sum. Plus, the second sum is pi. Remember, when I break it, I need to multiply pi. Keep pi multiplied by each term in the parentheses.
Oh, yes.
So pi times yi minus ey squared. Plus the last one, I can take 2, because it's a constant, I can take it in front of the sum, 1 to n of pi xi minus ex times yi minus ey. Right? So I didn't do anything but break this big sum into 3 smaller sums. This is the first one, this is the second one, this is the third one. Okay? Why did we do this? What is the first one?
Variance.
It's the variance of x. Very good. This one so this one, the first one, is the variance of x. So variance of x. What is the second one?
Variance of
Variance of
y.
y.
Variance of y. Very good, guys. You start getting it. And what's the last one?
Covariance of x and y.
Absolutely. If you look at that and this, that's exactly the same thing. So it's plus 2 covariance x and y. Exactly what we're supposed to show. Okay? Now, what is the direct implication of all these properties that we have discussed? Is the variance of a portfolio of 2 securities.
Right.
If we have a portfolio of 2 securities with the fractions W1 and W2, we already know that, and I'll write it in a very short format. We know that the variance of the portfolio is what? W1 square, variance of 1 square, plus W2 square, variance of 2 square, plus 2 W1, W2, covariance between 1 and 2. We already know this formula, right? But where is the formula coming from? From these properties, and we've seen if we have. So the variance of RP, where RP is what? Is the portfolio made of W1 invested in stock 1 and W2 invested in stock 2. I can write it now as variance of W1 R1 plus W2 R2, right? Well, I can think of this as x and this as y. right?
Yes.
Therefore, I can use the property that we have just demonstrated. And this is the variance of X, which is W1 R1, plus the variance of Y, which is W2 R2, plus 2 covariance of what? Of W1 R1, W2 R2. Right? Because our W1 R1 is X, or our X is W1 R1, and our Y is W2 R2. So far, so good?
Using the weighted average, you're extending the weighted average to the variance.
Well, I'm just using that formula, nothing
Yeah.
else, that property. Property 3 for the variance. So I'm using this formula.
Mhm.
However, I don't want to see variance of W1 R1. I want to see R1 separate because this R1 is the only random variable. W1 is just a constant.
Right.
But we have just demonstrated that if I multiply a constant by a random variable, the variance of dot product is what? It's a squared variance of the random variable. So in other words, what would be the variance of W1 R1? What's the variance of this?
The variance of the weighted average of R1.
Look at this, and look at this. I didn't put
Square
R,
of W1.
so it would be what?
W.
Square of W1.
So it would be W1 squared
Square.
times the variance
Variance
of
of R1.
R1, okay? Based on this property. I simply take the constant in front of it and square it,
Mhm.
and then multiply it by the variance of what's left. Right? Plus, what about the next one?
Square.
It's W2 squared var R2. And now the last one, well, for the last one, in fact, we need to use the fifth property, which is the property of the covariance. So we have 2, and now when we think of
AB.
W1 R1 W2 R2 is exactly as AX PY. It's exactly the same thing. So what do we do here? We take the constants in front of the covar,
Mhm.
and then the covar is left between R1 and R2. And that's exactly what we use in the classroom.
Yeah.
Because var R1 is nothing else but what we use as sigma 1 squared.
Right.
And var R2 is nothing else but what we use as sigma 2 squared. And this is covariance between R1 and R2. Our notation generally in the classroom is sigma 1, 2. And for var RP, usually we're using the sigma square P. So what we use on a regular basis in the classroom so far didn't have any theoretical framework. Now it does. Where are all these formulas coming from? The formula of the expected return of a portfolio or the formula of a variance of a portfolio. It comes from the properties of a random variable. The expected return, the expected value and the variance of the random variable. Okay, this is where they come from. Make sense? So not only so far did we learn the properties of the expected value and the variance of a random variable, but also how to apply these properties to find out the expected return and the variance of a portfolio of 2 risky assets. Okay? So far so good? Perfect. So I think it's time to take a break. Let's have a 15-minute break. It's 3:15, we'll have a break until 3:30. Yes,
Excuse me, sorry. On the comprehensives, do you have to break it down this way?
for the written component, yes.
Okay.
If the question asks you to show the properties, to
Show the
demonstrate the properties, yes,
You gotta show the proof.
yes,
Okay.
yeah. And I'm doing it because these are simpler demonstration for more complicated demonstration. Obviously, I'm not going to derive them on the board. I'm going to show them to you in the class notes, and then for the most difficult parts, I'll take those parts on the board. But these are simple properties. It's good to get your hands dirty. I thought that it's better if I do them on the board and just showing them to you on the screen. Okay? So we'll do few more derivations, and the rest will be simply I'll show you on the screen. Any other? Is it clear? Okay. Any questions before we have a break? No? Okay. 15 minutes.